Hello friends, I am Sandhya is currently studying in Sri Venkateshwara College of Engineering, Bangalore in the Department of ECE first semester. Subject is mathematics. Topic is vector calculus. Vector calculus. Introduction to vector calculus. Vector calculus is a branch of mathematics that deals with vector fields and differentiation and integration of vector function. It combines the concept of vectors from linear algebra with calculus, allowing for the analysis of multivariable function. This field is essential for various applications in physics, engineering, and computer science. Basic concepts of vectors. A vector is an entity characterized by both magnitude and direction. Vectors can be represented in different dimensions, commonly in two or three dimensional space. Basic operations with vectors include addition, subtraction, and multiplication. Vector functions. A vector function maps a real valued parameter to a vector functions. A vector functions maps a real valued parameter to a vector in n-dimensional space. The representation can be given as rt is equals to xt, yt, zt for three dimension. Vector functions are often used to describe curves in space. Limits and continuity. The limit of vector function is defined in a manner similar to scalar functions. A vector function is continuous if all its components functions are continuous. Understanding limits is crucial for analyzing vector fields and their behavior. Differentiation of vector function. The derivative of vector function describes the rate of change of the vector with respect to a parameter. The derivative is the computed component wise, leading to dr by dt is equals to dx by dt, dy by dt, dz by dt. This concept is fundamentally in physics, especially in motion analysis. Gradient of scalar field. The gradient is a vector operator that indicates the direction of the steepest ascent, in a sense maximum decrease of a scalar field. Mathematically, it is represented as delta f is equals to dou f by dou x, dou f by dou y, dou f by dou z. The gradient plays a key role in optimization problems in multivariable calculus. You can see another equation txyz is equals to yz square plus 3z square x plus 3z. This is an equation for gradient of scalar field. Divergence of a vector field. Divergence measures the rate at which stuff expands from a point in a vector field. It is defined as delta f is equals to dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. For a vector field, f is equals to f1, f2, f3. As in the image, you can see positive divergence indicates at a source, while negative divergence indicates at a sink. Curl of a vector field. Curl quantifies the rotational motion of a vector field around a point. It is defined as delta into f, resulting in a vector that describes the axis of rotation. The curl is essential in fluid dynamics and electromagnetism. A vector field is uniquely characterized by its divergence and curl. All vector fields can be classified in terms of their vanishing or non-vanishing divergence of a curl. For the following examples are shown below. A, B, C can see the directions of the curls mentioned here in the picture. Line integrals. Line integrals extend the concept of integration to vector fields along a curve. They can be used to calculate work done by force field along a path. The line integral is expressed as integration of CF dot dr, where C is the curve and F is the vector field. Surface integrals. Surface integrals generalize line integrals to two-dimensional surface in three-dimensional space. They are used to compute the flow of vector field across a surface. The surface integral is represented as double integration of SF dot ds, where S is the surface. The surface integrals equation here you can see in the given. The fundamental theorem of line integrals. This theorem relates the line integral of a conservative vector field to the potential function. It states that the line integral from point A to point B depends only on the values of the potential function at these points. The theorem simplifies calculation in vector fields significantly. Green's theorem. Green's theorem connects a line integral around a simple curve to a double integral over the region it encloses, and it is expressed given in the picture. This theorem has application in fluid flow and electromagnetic theory. Stokes theorem. Stokes theorem generalizes Green's theorem to three-dimensional relating surface integral to line integral. It states that the integral of the curl of a vector field over a surface equals the line integral around the boundary of the surface. This theorem is fundamental in physics, particularly in electromagnetism. And the Stokes equation is given in the picture. Divergence theorem. The divergence theorem relates the flux of a vector field through a closed surface to the divergence over the volume inside. Mathematically, it is expressed as flux SF into ds is equals to triple integration of V into delta F dV. This theorem is crucial in fields such as fluid dynamics and heat transfer. The divergence theorem, also is known as Gauss theorem, relates the flux of a vector field through a surface to the behavior of a vector field within that surface. Mathematically, it is stated as given in the equation. Applications of vector calculus. Vector calculus is widely used in physics to describe various phenomena, including electromagnetism and fluid dynamics. It has application in engineering fields such as mechanical and civil engineering. In computer graphics, vector calculus is used for rendering and modeling surface. Integration in higher dimension. Vector calculus extends to higher dimension, allowing for the analysis of the function in n-dimensional space. This involves concepts such as hyperplanes and hyperdimensional integrals. Understanding these concepts is crucial for advanced application in physics and mathematics. Challenges in vector calculus. While vector calculus provides powerful tools, it also presents challenges such as managing complex boundaries. Working with discontinuous function can complicate integration and differentiation. Mastery of the vector calculus requires a solid understanding of both calculus and linear algebra. Vector calculus is a fundamental area of mathematics with vast application. Its principles are essential for understanding and modeling dynamic system in various fields. A stronger foundation in vector calculus opens door to advanced studies in mathematics, physics and engineering. Thank you.